Welcome to AIHL complex numbers tutorial. So in this video, what we'll be doing is we'll be trying to understand the basics of complex numbers. So firstly, before starting the topic, we need to understand where did the theory of complex numbers come from in the first place. So actually the theory came from the study of reduced polynomials, or in fact the reduced cubic polynomials. But the thing is, something which is more relatable to us is the theory of quadratic equations, and that is what is expected with regards to the AIHL syllabus. Basically, what we'll do is we'll try to understand how complex numbers originated from the theory of quadratic equations. So we'll start by considering a quadratic equation. For example, x squared minus 2x minus 3 is equal to 0. So this is a quadratic equation, and finding the two roots of this is not that difficult, which is x is equal to minus 1 and x is equal to 3. So the result, which was known to mathematicians at that time, was that if I have a quadratic equation of the form ax squared plus bx plus c is equal to 0, so the sum of the roots will be minus b by a, and the product of the roots will be c by a. These were the known results, which actually you can verify for the quadratic on the left as well. Like if I add the roots, which is 1, minus 1 and plus 3, I'll get 2. And even if I do minus b by a, which is minus of minus 2 by 2 into, minus of minus 2 by 1, which gives me 2. So, which is verified on the left hand side. Similarly, the product identity. So the product of minus 1 and 3 is minus 3. And the product of and c upon a, which is minus 3 upon 1, also gives us minus 3. So these two were the results known. But the thing is, there was a problem, because it's very much possible that a quadratic equation has no roots as well. So for example, if I have a quadratic equation x squared minus 2x plus 4 is equal to 0. So for this quadratic, if I try to find the sum of roots without actually finding the roots, the sum of roots will be minus of minus 2 upon 1, which is again 2. The sum of roots is 2. And the product of roots will be c divided by a, which is 4 divided by 1, which is 4. So what I'll do now is I'll try finding the roots of this quadratic equation. So I'll use the formula method for it. So I'll get x is equal to minus b plus minus root of b squared minus 4ac minus b squared minus 4ac over 2a. So this gives me 2 plus minus root of 4 minus 16 upon 2, which gives 2 plus minus root of minus 12 over 2. So there's a slight problem here. The thing is, the two roots are 2 plus root minus 12 upon 2 and 2 minus root minus 12 upon 2. So actually there are no real roots for this equation, because square root of minus 12 doesn't exist by definition. But the thing is, the sum of roots is still 2 and the product of roots is still 4. So how is it possible that two non-existent things are adding up to 2, adding up to a real number and multiplying to a real number as well? So to take this theory into account, we define I, which is square root of minus 1. So now what we'll do is we'll write both the roots in terms of I. So if I is root minus 1, root of minus 12 can be written as root minus 1 into root 12. And root minus 1 is I. So root of minus 12 can be written as root 12 into I. So my roots will be, the first root will be 2 plus root 12 I over 2. And the second root will be 2 minus root 12 I over 2. And it's easily verifiable that if I add these two roots, I'll get 2. And similarly, the product will also give me 4. So this is where complex number starts from, by defining a variable I, which is square root of minus 1. So the first thing is we'll try to understand the properties of I. So I'll just write it down, properties of I. So I equals square root of minus 1. That's the definition. So if I squared both sides, I'll get I squared as minus 1. And then I cube will be I squared into I, which is minus 1 into I, which is minus I. So minus I minus 1. And I raised to 4 will be I squared into I squared, which is minus 1 into minus 1, which is 1. So now if I have to find I raised to 5, what I can do is I can write it as I raised to 4 into I raised to 1 using the laws of indices, and I raised to 4 is unity, so which gives me I. Similarly, I raised to 6 can be split up as I raised to 4 into I squared. So the thing is, since I raised to 4 is 1, I raised to 6 is the same as I squared, which is minus 1. Similarly, I raised to 7 is same as I cube, which is minus I. Similarly, I raised to 8 is 1. And the cycle repeats in steps of 4. So finding I raised to 66 is a very easy task. What I'll do is I'll find the closest multiple of 4 to 66, so which is 64. So I'll split it as I raised to 64 into I squared, which gives me 1 into I squared, which is the same as I squared minus 1. Okay, so these were certain things related to the properties of I. Next thing is the definition of a complex number. So complex number is defined, a complex number z is defined as a number which can be written in the form of a plus ib, where a and b belongs to real numbers. This is the definition of a complex number, and this form is called the Cartesian form. Cartesian form of the complex number. So in this case, the variable a is written as real part of z. Sorry, the constant a is written as the real part of z, and the constant b is written as the imaginary part of the complex number z. So the first operation which we'll understand in complex numbers is addition and subtraction. Addition and subtraction. So if I have a complex number a plus ib, and I have a second complex number z2, which is c plus id. So adding the two complex numbers is a pretty easy task. What I'll do is I'll add the real part with the real part and the imaginary part with the imaginary part. So this will become a plus c plus I, common out, b plus d. So for the new complex number, which is the addition, z1 plus z2, the real part is a plus c and the imaginary part is b plus d. No catch here. It's a very straightforward result. And similarly, in similar procedure, subtraction also works. So if I want to write z1 minus z2, it's a minus c plus I times b minus d. So I can write it down again that real part of z1 minus z2 is a minus c, and the imaginary part of z1 minus z2 is b minus d. Okay. Next, we'll go to multiplication. Multiplication. So if I have a complex number z1, which is 1 plus I, and a complex number z2, which is 3 plus 4i, and if I have to multiply z1 into z2, so the expansion, we'll follow the normal expansion procedure, which is a 4-step expansion in this case. So which will give me 1 into 3 as 3, 1 into 4i as 4i, I into 3 as 3i, and 4i into I as 4i squared, which is I squared is minus 1. So which is 3 plus 4i plus 3i minus 4, which is minus 1 plus 7i. So for the complex number z1 into z2, it's minus 1 plus 7i, the real part, and the imaginary part is, sorry, my bad. The real part is minus 1 and the imaginary part z1 into z2 is, of z1 into z2 is 7. So this is basic multiplication of complex numbers. Now moving further ahead, we'll understand a simple concept which is of the conjugate. Conjugate. So if I have a complex number a plus ib, the conjugate of the complex number is defined as a new complex number, which is a minus ib. That means the real part remains the same while the imaginary part changes sign. So if z is a plus ib, z star is, or z conjugate, sometimes it's written as z bar also, like this. Both of them means the same thing. So the conjugate is defined as a minus ib. So with respect to the conjugate, there's a very interesting property of a multiplication of complex number with its conjugate. So if I have a complex number z and I'm multiplying it with its conjugate, so I'll start with the general case here, which is a plus ib into a minus ib. So I'll directly make use of the identity that a plus b into a minus b is a squared minus b squared. So this becomes a squared minus ib the whole squared, giving me a squared minus I squared b squared, which is a squared plus b squared. Now the result is actually straightforward, but the thing is, there's one very important thing to note here. And the important thing to note here is that if I'm multiplying two complex numbers, or if I'm multiplying a complex number with its conjugate specifically, the multiplication yields in a real number. So I can see that if I'm multiplying z with its conjugate, I get a real number here, which is a squared plus b squared, which is independent of I. Independent of I. Which is in fact not always true. Because if I'm multiplying two random complex numbers, for example, 1 plus I with 3 plus 4i, the resultant multiplication gives me a complex number itself with a non-zero real part. Non-zero imaginary part, my bad. So this is a very important property related to the conjugate of a complex number. And this will help us actually to understand the division operation in complex numbers better, which is the next thing which we'll do. So we'll just move ahead with division. So I'll define a complex number 1 plus I and another complex number z2 as 3 plus 4i. So if I have to find the division z1 upon z2 upon z1, so that can be written as 3 plus 4i upon 1 plus I. So my objective now is to write the division z2 upon z1 in the form of a plus ib. That means the real part of z2 upon z1 should be visible and the imaginary part of z2 and z1 should be visible separately. So the first process, what I'll do is there are actually two methods of doing this. So firstly, what we'll do is, since we've studied the conjugate literally a second back, I'll make use of that concept here. So what I'll do is, I'll do a kind of a rationalizing step. I'll multiply the denominator with the conjugate of it. So 1 plus I I'll multiply with the conjugate of it, which is 1 minus I. And since I can't just multiply the fraction only in the denominator, to make it even, I'll have to multiply 1 minus I in the numerator as well. So this is what I'll do in my first step. Now the objective of doing this is that if I'm in the denominator, if I'm multiplying a complex number with its conjugate, so my denominator will actually become free of I. There'll be no I term in the denominator. So I'll just write it down here. No I term. Now I'll move ahead with my multiplication. So in the numerator, I'll get 3 minus 3i plus 4i minus 4i squared upon 1 squared minus I squared, which will give me 3 minus 3i plus 4i plus 4, since I squared is minus 1. Similarly, in the denominator, I'll get plus 1 like this. So 3 plus 4, collecting the real terms and the imaginary terms in the numerator, which will give me 7 plus I upon 2. So if I write the real and imaginary part separately, I get the real part of z2 upon z1 as 7 over 2, which is 3.5. And the imaginary part of z2 upon z1 as half, which is 0.5. So this is how the division operation can be carried out. So this is the first method actually. Now I'll show you the second method of finding the division of two complex numbers in the form of a plus ib. So I'll consider the same example. So method 2, 3 plus 4i upon 1 plus I is equal to a plus ib. I'll assume that the multiplication yields a general complex number a plus ib. So my objective now is to find the constants a and b. So for that, what I'll do is I'll multiply or cross multiply 1 plus I to the other side. So I get 3 plus 4i equals 1 plus I into a plus ib. Expand it up, which gives me a plus ib plus ia plus I squared b. So 3 plus 4i is equal to I squared is minus 1, which gives me a minus ib plus I times a plus b. So now I get an equality in terms of two complex numbers. So in this case, what we'll do is we'll compare the real part with the real part and the imaginary part with the imaginary part. And this is a very powerful result. So this result I'll just summarize here. Equality of complex numbers. So two complex numbers can be equal only if their real parts and their imaginary parts are both equal. So in the general case, if I'm equating a plus ib to another complex number c plus id, so this equation yields me two conditions. Firstly, a is equal to c, and the second one is b is equal to d. Since both the real parts and the imaginary parts of the two complex numbers have to be equal. So in this case, the equality condition will give me two equations. The first one is a minus b equals to 3, and the second equation as a plus b equals to 4. So solving this simultaneous equation, I'll get a as 7 upon 2 and b as half, which I got using my first method as well, 3.5 and 0.5. So moving on to the question. So the question is, find the complex number z such that 4z minus 23 is equal to 5iz plus 2y. Okay, so what I'll do is, the first thing is I'll assume that z is x plus iy, a general complex number. So my equation becomes 4 into x plus iy minus 23 is equal to 5i times x plus iy plus 2i. Simplifying on the left hand side, I'll get 4x plus 4iy minus 23 equals 5ix plus 5y I squared plus 2i. So this becomes 4x minus 23 plus I times 4y is equal to 5ix, and I squared is again minus 1, so this becomes minus 5y plus 2y. Collecting the real parts on the left hand side, which is 4x minus 23 is the real part, and the imaginary part, which is 4y, equals on the right hand side, it's minus 5y as the real part and the imaginary part as 5x plus 2. So comparing the real part with the imaginary part, I can say 4x minus 23 equals minus 5y. That's my first equation. And my second equation is 4y equals 5x plus 2. That's my second equation. So my equations become 4x plus 5y equals 23 and minus 5x plus 4y equals to 2. Now these two equations I'll solve in the simultaneous solver in the GDC. So I'll press menu. Equations F1, which is simultaneous solver, number of unknowns 2. It's 4, 5 and 23 for the first equation. 4, 5 and 23. And for the second equation, it's minus 5, 4 and 2. So minus 5, 4 and 2. I'll press solve. I'll get 2 and 3. So x is equal to 2 and y is equal to 3. So my complex number z is 2 plus 3i. That's my answer. Moving on, the next question is, find the complex number z such that 2z plus I z conjugate equals 1 minus 7i. So again, I'll assume the complex number as z is equal to x plus iy. Substituting, I get 2 times x plus iy plus I times conjugate, which is x minus iy, equals 1 minus 7i. So expanding, I get 2x plus 2iy equals ix minus I squared y is equal to 1 minus 7i. So, sorry, there's a plus sign here. So I squared is minus 1, so the real part is 2x plus y, and the imaginary part is 2i times 2y plus x. So again, I get my two equations, which is the first one is 2x plus y equals to 1, and the second is 2y plus x equals to minus 7. Again, I'll solve both the things on the JDC here. I'll press exit. So 2, 1 and 1. 2, 1 and 1. Second thing is 2, 1, 2 and minus 7. So 1, 2 and minus 7. I'll press solve. So 3 and minus 5. So x is equal to 3 and y is equal to minus 5. So my complex number is 3 minus 5i. That's my answer here. The next section is representation of complex numbers. Representation. So if I have a real number, for example 2, so the real number 2 can be represented on the one-dimensional number line. So suppose there's a 0 here, so 2 will be somewhere on the right here. Similarly, minus 1 can be represented somewhere on the left here. Root 2, which is 1.414, can be represented somewhere between 0 and 2 here. So all the real numbers can be represented on a one-dimensional real axis. But that's not the case for complex numbers, because complex numbers have an imaginary part as well. So what we do is we use an extension of the real number line. So along with the real number line, what we do is we, perpendicular to the real axis, we make an imaginary axis. So this plane here, where on the y-axis or the vertical axis we have the imaginary part, and on the horizontal axis we have the real part. That plane is called the Argand's plane. So complex numbers are represented on the Argand's plane. So if I have a complex number, for example 1 plus 2i, so the real part is 1 and the imaginary part of z is 2. So what I'll do is on the real axis I need 1 and on the imaginary axis I need 2. So this is 1 comma 2 here. So the complex number will be represented like an arrow starting from the origin till the point, like this. So this is my complex number z, which is 1 plus 2i. So this is the first quadrant, the second quadrant, the third quadrant, and the fourth quadrant. So my complex number can lie in either of the 4 quadrants depending on the sign of the imaginary and the real part. Next is the definition of the magnitude or the modulus. In fact, it's better we call it the modulus because it is called the modulus. Modulus. So modulus is basically the length of the complex number in the Argand's plane. So for example, if I consider the example of 1 plus 2i, which is the complex number represented on the left side. So the length of this complex number can simply be found by using the Pythagoras theorem. So the modulus of z, the notation is the absolute value notation like this. So modulus of z is nothing but square root of 1 squared plus 2 squared, which is basically found using the right angled triangle here, which is the Pythagoras theorem. So in this case, I get the modulus as root phi. The argument is the angle made with the positive real axis. So if this is my complex number, the argument is this angle made with the positive real axis. The positive real axis is basically the one on the right hand side. The one on the left hand side is the negative real axis, because here the complex number is purely real, but the thing is its real part is negative. So the argument in this case can simply be found by using basic trigonometry. So I can say argument, or capital A argument of z is equal to tan inverse 2 upon 1, which gives me, you can find that answer in the GDC here. So I'll press menu, go to run matrix. So I'll press shift tan inverse, put the fraction thing in, 2 upon 1, which gives 1.107 because my calci is in degrees as of now. So what I'll do is, sorry, my calci is in radians as of now. So I'll press shift setup and change my calci to degrees. And then again press execute. So which gives me 63.4. So 63.4 degrees is the argument of this complex number. Okay, so this was the case when my complex number was in the first quadrant. Suppose my complex number is now in the second quadrant. So I'll consider a complex number in the second quadrant as Z1 or Z2 equals minus 1 plus root 3i. So since this complex number is in the second quadrant, I've denoted by it's denoted by an arrow somewhere here, pointing in the second quadrant. So the modulus of this complex number is again written by the Pythagoras theorem. So it will be minus 1 square plus root 3 square, which is square root of 1 plus 3, which is 2. So the length of this complex number is 2. Now the argument is again the angle made with the positive real axis, which is this blue angle denoted in this diagram here. So what I'll do is, in this case, I'll directly find the argument in the GDC. So I'll press options, complex, and then ARG argument, and I'll open and close a bracket here. Inside that bracket, I'll write my complex number, which is minus 1 plus shift root 3 I, which is 120 degrees. So I'll better keep my calci in radians because that's something which will be used often. So I'll press radians here. 2 pi by 3. So the argument of Z2 is 2 pi by 3 radians. Next, I'll consider complex number in the third quadrant. So Z3 equals minus 1 minus root 3i. So that is a complex number with both real and imaginary part negative, so which is in the third quadrant here. So the argument is, so the modulus firstly is Pythagoras theorem, which is square root of minus 1 square plus minus root 3 squared, which is 2 again. And the argument in this case, I'll try finding on the GDC. So I'll press arg, open close brackets, minus 1 minus shift root 3i, which is minus 2 pi by 3. So what the calci is doing is, instead of considering the argument is plus this anti-clockwise angle from the positive real axis, the calci is considering the argument as an angle counted clockwise from the positive real axis, which is this way. So the calci is doing this because the calci is always giving you the argument in the principal domain or the principal range. And the principal range for the argument is minus pi excluded till pi included. So when calculating angles as positive, the argument can't exceed 180 degrees. So in this case, considering the blue angle is not possible because that angle is exceeding 180 degrees in positive. So instead what I'll do is I'll count the angle as negative but less than minus pi. Sorry, greater than minus pi. So in this case, the argument is minus 2 pi by 3. So I'll write it here. Argument of Z3 is equal to minus 2 pi by 3. That's my angle or the argument here. Next, the fourth quadrant, which is 1 minus root 3i. So 1 minus root 3i is a complex number in the fourth quadrant. Again, the same procedure, finding the modulus using the Pythagoras theorem. So 1 square minus root 3 squared, which is 2. And the argument, if I find on the GDC again, I'll get it as minus pi over 4. So minus pi over 4 denotes this angle calculated clockwise from the positive real axis. This is imaginary and this is real. Okay, so this is basically the concept of modulus and argument of a complex number. So I'll just summarize it here, especially the modulus formula. So if I have a general complex number z, which is x plus iy, so the modulus of z can be written as square root of x squared plus y squared. And if I square this result, square both sides, I'll realize that the modulus square is nothing but x squared over y squared. And x squared over y squared can be obtained by doing one more operation, which is multiplying a complex number with its conjugate. If I multiply x plus iy with x minus iy, I'll get x squared plus y squared. So one more result is that modulus square is z into z conjugate. Cool. Let's move on to the next session, which is polar form of a complex number. So the polar form is also called the modulus and argument form, because in this case what we're doing is we're defining the complex number in terms of its modulus and argument, which we'll see soon. Modulus argument form. So the first form which we saw was the Cartesian form, which is a plus ib form, where you represent the complex number in terms of its real and imaginary part. So if I have a complex number a plus ib, so in the Cartesian form what you do is you mark the point corresponding to the real part and imaginary part here, and you connect it by an arrow like this. This is basically the Cartesian representation of a complex number. So as I said, the polar form is called the modulus and argument form. So what I'll do is I'll define two variables corresponding to the modulus and argument. So I'll use the variable r for the modulus, denoting the length, and the variable theta for the argument, denoting the angle from the positive real axis. So if I consider the right angle triangle formed here, two results are pretty straightforward to prove. The first result is cos theta equals a over r, so a is equal to r cos theta, and the other result is that b equals to r into sine of theta. So substituting the values of a and b in terms of r and theta into my Cartesian form, I'll get z is equal to r cos theta plus I r sine theta. And taking r common, I'll get cos theta plus I sine theta. So this form here is called the polar form of the complex number. The polar form is also called the cis form of the complex number, due to the existence of c for cos, I for I, and s for sine. So an acronym or a short form for the polar form is r cis theta. So instead of writing the whole thing as cos theta plus I sine theta, we use an acronym which is cis theta. So this is my complex number represented in polar form in terms of my modulus and argument. So if I have a complex number 1 plus I, exercise. So if I have a complex number 1 plus I, the modulus of the complex number is square root of 1 squared plus 1 squared, which is root 2. And the argument of the complex number is tan inverse 1 over 1, which is the first quadrant thing, which you can find on the GDC as well. So I'll get that as pi by 4. So my complex number in cis form can be written as r cis pi over 4. Oh, sorry, root 2 cis pi over 4. So this is the polar form of my complex number. Root 2 cis pi over 4. And this can be achieved directly on the GDC as well, because there's a feature in the GDC which directly converts the Cartesian form into polar form. So if I have the complex number 1 plus I, right from the beginning I'll press options complex and then further options f6 and then r theta. So I'll just execute, I'll get both the modulus and argument of the complex number. So that's root 2. And after this angle sign, I have pi by 4 written, which is my argument. So, which actually verifies my calculations here. So I get root 2 cis pi over 4 as the polar form of the complex number. There's a very important reason for converting any complex number into its polar form, and that reason is due to the properties of cis theta. So that's what we'll see next. Properties of cis theta. So the first property is the multiplication property. So if I have cis A into cis B, so that is nothing but cis A plus B. Second, which is division, cis A upon cis B, which is cis A minus B. And the third property is that if I have cis A raised to some real number n, it will give me cis n times A. The third property is actually an extension of the first property only. So basically, if I have to find cis A raised to n, it's basically cis A multiplied with itself n times. So since multiplication turns into addition, the result is nothing but cis n times A. So these are the three important properties of cis theta. And if you look at them very carefully, these properties of cis are actually quite similar. In fact, they're actually the same as the properties of exponents, or basically the laws of exponents. And soon, in a minute, you'll understand why the properties of cis theta are same as the properties of an exponent. Okay. So if I have to multiply two complex numbers, so for example, if I have a complex number 1 plus I, and if I have another complex number, okay, I'll write both the complex numbers in polar form first. So if I have a complex number 2 cis pi by 4, another complex number which is root 3 cis pi over 8. So if I'm multiplying the two complex numbers z1 into z2, the multiplication becomes quite simple in the case of polar forms, because I'll have to multiply 2 with root 3, which is 2 root 3, and cis pi by 4 into cis pi by 8, which will actually give me cis pi by 4 plus pi by 8, which is 2 root 3 cis 3 pi by 8. So this is basically the polar form of the multiplication of two complex numbers. Division also works the same way. So for example, if I have to find z1 upon z2, so that will be 2 cis pi over 4 upon root 3 cis pi over 8, which will give me 2 upon root 3 cis pi over 4 minus pi over 8. Writing the complex numbers in polar form actually helps to understand properties of modulus as well. So if I have two complex numbers, one is r1 cis theta 1 and another is z2 is equal to r2 cis theta 2. So if I'm multiplying the two complex numbers z1 with z2, I'll get r1 cis theta 1 into r2 cis theta 2, which gives me r1 into r2 cis theta 1 plus theta 2. So as of now, I'll focus on the moduli, or the modulus of the two complex numbers here. So one important property which I can see is that if I consider the whole modulus z1 into z2, that's nothing but the same as modulus of z1 into modulus of z2. So this result is true. In fact, it works for more than two complex numbers multiplied as well. Similarly, the same thing for division. If I have two complex numbers, which is r2 cis theta 2, and I divide it in this case, so z1 upon z2, which will be r1 cis theta 1, so which is r2 upon r1 cis theta 2 minus theta 1. So modulus of z2 upon z1 is modulus of z2 upon modulus of z1. So this is my one more property of the modulus of complex numbers. Next, we'll move on to the Euler's formula. So Euler proved the identity that e raised to I theta can be written as cos theta plus I sin theta, or basically cis theta, provided theta is in radians. Because the identity, he proved it using Taylor series, and Taylor series is a concept in calculus which is valid only if theta is in radians. So this Euler's identity is valid when theta is in radians. So if I have a complex number root 2 cis pi by 4, in polar form. So the same complex number is in Euler's form can be written as root 2 e raised to I pi over 4. And one important aspect of using the Euler's form is the ease at which we can put the complex number in the GDC. So for example, writing root 2 says pi by 4 is a bit difficult because we'll have to put that sign in. But writing root 2 e raised to I pi by 4 is way simpler. So which is root 2. So I write this complex number, I'll press shift ln e raised to, then I'll press I here, open close, and inside I'll write the fraction. So I'll write shift pi over 4. Press execute, which is 1 plus I, which is my Cartesian form for this complex number. So this is called the Euler's form of the complex number. And one thing which I asked you to note earlier was that the properties of cis were actually very similar to the properties of exponents. And that was because of the fact that cis theta is actually similar or same as e raised to I theta. And e raised to I theta is an exponent. So the properties of cis and exponent are in fact very, very similar, in fact the same. Okay. So next we'll handle some questions. First question is root 2 cis 3 pi by 8 is equal to w cis and w cis 2 n pi by 24 are two complex numbers. Find z raised to 6 in Euler's form. Okay, so z is root 2 cis or e raised to I 3 pi by 8 raised to 6. So which becomes root 2 raised to 6 e raised to I 3 pi by 8 into 6, which is actually 6 3s are 18 pi over 8. And 18 pi over 8 is 2 4s are 2 9s are, which is 9 pi over 4. So and root 2 raised to 6 is 2 raised to 1 by 3 raised to 6. And I'll write this as e raised to I 9 pi by 4 only as of now. So which is 2 raised to 2, which is 4 e raised to I 9 pi by 4. But the problem is my theta has to be in the principal argument range. It has to be in the principal argument. So what I'll do is I'll try understanding how my complex number looks like. So 9 pi by 4 is a number which is more than 2 pi. That means I'm taking a whole revolution and then coming back in the first quadrant approximately. So this is my complex number here. The length is 4. And if I consider the complex number in the principal argument, what I'll do is I'll just disregard the first rotation and consider the remaining angle as my argument. So that remaining angle is 9 pi by 4 minus 2 pi, which is 4 2s are 8 pi by 4. So my complex number is basically 4 e raised to I pi over 4. This is my complex number in polar form. And this could have been achieved directly in the GDC as well. So I could have written root 2. I've already written root 2 e raised to I 3 pi by 8. So shift x square root 2 shift ln shift I bracket 3 shift into 10 pi by 8. I'll open a bigger bracket and close a bigger bracket and write raised to power 6. Raised to 6. And the thing is, I want my resultant answer to be in polar form. So I'll put this r theta syntax separately towards the right. So I get 8 cis pi over 4. Oh, my bad. This was 2 raised to half. So this is 2 raised to half raised to 6, which is actually 2 raised to 3, 8. So I'll make the correction here. So my complex number is 8 e raised to I pi over 4. The B part is saying that find the value of w into z raised to 4 for n is equal to 5. Give your answer in the form r e raised to I theta. So w into z raised to 4. So w into z is the multiplication of these two. For n is equal to 5. So it will be 2 root 2 cis addition of the argument, which is 3 pi by 8 plus this 5 pi by 24. So this becomes 2 root 2 cis 8 into 3. So 14 pi by 24. So 2 12s are and 2 7s are. So 2 root 2 cis 7 pi by 12. And 7 pi by 12 is in the principal argument. So I'll write this as 2 root 2 e raised to I 7 pi over 12. This is my answer for the second part. Now the third part is find the smallest integer n greater than 9 such that z upon w belongs to real numbers. So z upon w, which is basically root 2 cis 3 pi over 8 and 2 cis n pi by 24. So if I divide, I'll get 1 over root 2 dividing the modulus and subtracting the arguments. So 3 pi by 8 minus n pi by 24. So the thing, our complex number should belong to positive real numbers. So not positive real numbers, actually just real numbers. So that means it can either be pointing towards the left or be pointing towards the right. So that means the possible values of the argument is 0, 180 pi, 362 pi, 3 pi, 4 pi, so on and so forth. And similarly on the negative side, minus pi, minus 2 pi, so on and so forth. So what I'll do is I'll equate the argument, which is 3 pi by 8 minus n pi by 24 to 0 first. So if I equate it to 0, I'll get n as 24 into 3, 9. But the thing is, they are saying n has to be greater than 9. So what I'll do is logically, I'll move on to the next positive value, which is 3 pi by 8 minus n pi over 24 is equal to pi. And now to make n the subject, I'll take this whole term on the right and pi towards the left. So I'll get 3 pi by 8 minus pi is equal to n pi over 24. But one thing which we realize here is that 3 pi by 8 minus pi is a negative number. So which will lead to a negative value of n. But the thing is, it's given that n belongs to positive integers here. So the same will be the case if I consider 2 pi, 3 pi, 4 pi, all the positive values. I'll get a negative values of negative values of n basically. So the procedure actually works towards the negative values. So what I'll do is I'll equate 3 pi by 8 minus n pi by 24 to minus pi. And now I'll get 3 pi by 8 plus pi equals n pi over 24, which is 11 pi over 8 is equal to n pi over 24. Cancel pi and pi. I'll get n as 33. So the answer is 33 for the C part of this question. The next topic is transformations using complex numbers. So transformations. So earlier we had seen that if I have a complex number which is of the form r cis theta, okay, and I'm multiplying this complex number z, which only the cis value, which is cis alpha. So what happens is it's basically r cis theta multiplied with cis alpha. So this cis theta will multiply with cis alpha, and using the laws of cis or the properties of cis, it becomes r cis theta plus alpha. So what happens is my complex number z, which is r cis theta. So this is r theta. If I'm multiplying it with cis alpha, what happens is the modulus remains r only. That means my complex number is of the same length r, while the argument increases by alpha. So that effect is basically of rotation by anti-clockwise by alpha. So if I'm multiplying a complex number z with cis alpha, the transformation is anti-clockwise rotation by alpha, by angle alpha. Similarly, if I'm multiplying z with cis of minus alpha, so the effect is similar, but the thing is it'll rotate the other side, or basically in the clockwise direction. in the clockwise direction. So this is clockwise rotation by angle alpha. Next, the same complex number z, if I'm multiplying it with just 2. So what I'll get is 2r cis theta. So in this case, my argument is unaffected. That means my complex number is pointing in the same direction. But the thing is, one difference which I can see is in the modulus. My modulus becomes double of what it was. So my complex number is of length 2r, while the angle remains the same. So this transformation is basically called an enlargement by scale factor 2. This is what this transformation is called. It's called an enlargement by scale factor 2. So as of now, we've seen two transformations. One is enlargement by scale factor 2 and one is rotation clockwise and anti-clockwise. What happens if I try doing both of them together? So the complex number, if I multiply it with 2 cis alpha. So if I'm multiplying the complex number with 2 cis alpha, the resultant complex number will be twice in modulus, which is 2r, and the rotation effect will also come in. So my argument will become theta plus alpha. So I have a combined effect. The combined effect is my complex number, which is with modulus r and argument theta, will become twice of what it was in terms of length, and will also rotate alpha degrees or alpha radians in the anti-clockwise direction. So both the transformations happening together. Now we've seen enlargements and we've seen rotations. So now we'll see the easiest of the transformations, which is translations. And translations in complex numbers can just be achieved by adding and subtracting complex numbers. So if I have a complex number which is 1 plus I, and I'm adding it with the complex number 2 plus 3i. So the resultant complex number will be 1 plus I plus 2 plus 3i. So which will give me 3 plus 4i. So that means my complex number is actually shifted towards the right by 2 units and up by 3 units, which is visible by the real and imaginary part of the addition complex number. So my real part, which was 1 first, has become 3, and the imaginary part, which was 1 first, has become 4. So if I want to represent it on a diagram, this is my complex number, which is 1, 1, both real and imaginary part is 1, moving towards the right by 2. So right 2 units, up 3 units. So it has come to a new position here, which is 3 plus 4i. So roughly drawing it here like this. So this is basically translations in complex numbers. Now we'll understand certain standard transformations, which is achieved using I. So I is basically a complex number which points up, which is purely imaginary and is of length 1. So I in cis form can be written as 1 cis pi over 2, because pi over 2 is the argument, or 90 degrees. So I can be written as 1 cis pi by 2 or just cis pi by 2. So if I'm multiplying any complex number with I, for example, I into z, the same z, the earlier z, which is r cis theta. So in this case, since z is cis pi by 2, my resultant complex number will be r cis theta plus pi by 2. That means multiplying any complex number with z rotates the complex number pi by 2 radians anti-clockwise. So from r theta, it will become r theta plus pi by 2. So multiplying with I rotates the complex number pi by 2 radians anti-clockwise. The last application of complex numbers is addition of sinusoidal functions. So if I have two sinusoidal functions are basically trigonometric functions, sine and cosine functions. So in that case, to add sine and cosine functions of same frequency or the same period, I'll use the concept of complex numbers. So that I'll make you understand why this question, which is two voltages or basically AC voltages uh, are of the form V1t is equal to 12 cos 20t and V2t is equal to 18 cos 20t plus 5. So one thing to observe is that both the voltages have the same frequency or the same time period. So in this case, to add these two voltages, what I can do is I can use the concept of complex numbers. So firstly, I'll just write down the addition plainly. So V1t plus V2t is equal to 12 cos 20t plus 18 cos 20t plus 5. So I have to write the addition of these two cosine functions as a single cosine function. So one thing to note was that if my complex number is r says theta, the real part of this complex number was r cos theta and the imaginary part of this complex number was r sine theta. So what I can do is I can write 12 cos 20t as the real part of the complex number 12 cis 20t or e raised to I 20t. Similarly, I can write 18 cos 20t plus 5 as the real part of 18 e raised to I 20t plus 5 in brackets like this. Now what I'll do is, for the first term, I'll let it be as it is. For the second term, I'll expand it up. So I'll get 18 e raised to I 20t plus 5i. And then using the laws of indices, I can just split up the second term again as e raised to I 20t into e raised to I 5i. And if I take e raised to I 20t common, I'll get 12 plus 18 e raised to I into 5. And 12 plus 18 e raised to I into 5, I can add up in my GDC. And the addition I want in polar form. So this syntax is something which I'll have to consider. So that's what I'll do. So this is 12 plus 18 and my galaxies in radians. Okay, shift e raised to I 5. What's this? Okay, so the syntax error is coming due to the because the calci cannot recognize whether it's I is multiplied with 5 or not. So I'll just put a bracket here. And yeah, now I get the answer 24.3 e raised to I minus 0.789 or 790, rounding it off. So this becomes real part of e raised to I 20t, and this has 24.3 e raised to minus 0.790 I. Minus 0.790 I. Okay. Now I'll multiply e raised to I 20t with this e raised to minus 0.790 I term. So I'll get real part of 24.3 e raised to I 20t minus 0.790. So now this thing is basically the cosine part of this complex number. So it gives me 24.3 cos 20t minus 0.790. So this is basically the addition of these two cosine functions. This 12 cos 20t plus 5 plus 18 cos 12 cos 20t plus 5 plus 12 cos 20t plus 18 cos 20t plus 5 is equal to 24.3 cos 20t minus 0.790, whatever. So now they are saying hence write down the highest voltage in this circuit. So the highest voltage in this circuit is 24.3.